Okay, so welcome back. So in this video we will start exercise 4.6. So exercise 4.6. So exercise number, we want to examine the consistency of the system of equations in exercises 1 to 6. So let me see how they have done this over here. Okay. Okay, so so let's say that you have a system of equations, and that is, for example, that is question number 1, and you have x plus 2y is equal to 2, and 2x plus 3y is equal to 3. That's the system of equations that you have. Okay, so basically a system of equations is called consistent if you have a unique solution. So a unique solution means that you have basically either 2 lines or 3 lines where the lines basically intersect one another at a distinct point in the coordinate plane. Meaning that the unique solution means that the lines intersect at a distinct point. So if the lines are supposed to intersect at a distinct point, that means that the lines need to have basically a different slope. It means that the lines have different slopes, and what that means is that basically the ratio of the x and y's are different, meaning that the slope of this line, for example, x plus 2y is equal to 2. The slope of this line is basically you can say that basically if I write this 2y is equal to negative x plus 2, and y is equal to divide by 2 negative 1/2 x plus 1. So the slope of this line, as you can see, if I write this equation in the form ax plus by is equal to c, for example, then the slope of this line becomes negative m, becomes basically negative a by b. As you can see over here, a is 1 and b is 2, and the slope of the line has become negative 1/2, meaning negative a by b. So these have to be, a by b has to be different, meaning that if I call this, for example, if I call my system of equations as a1x plus b1y is equal to c1, and a2x plus b2y is equal to c2, a1 to negative a1 to b1, or negative a to b, has to be not equal to negative a2 to b2. And of course I can cancel out these two negative signs from both sides of this equation. I have a1 to b1 not equal to a2 to b2, and of course this inequality, it's actually not an inequality, but it's a meaning that these are not equal. Inequality would be something else, of course. Then if I cross multiply, I will get A1 times B2 is not equal to A2 times B1. And if I divide by A2 both sides of this equation, I'll get A1 by A2 is not equal to times A1 by I'm sorry, if I divide by B2, for example, I'll get A1 B2 divided by B2 is not equal to A2 B1 by B2, right? And so I will get basically B2 and B2 cancel out. I have A1 is not equal to A2 times B1 divided by B2. If I still divide by A2, I will get basically A1 to A2 is not equal to A2 to A2 times B1 to B2. And this would be 1. And therefore you would have A1 to A2 is not equal to B1 to B2. B1 to B2. Which means that when you say that A1 to B1, when you say that basically A1 to B1 is not equal to A2 to B2, that also means that you can write this as, or let me make it simpler. When you say that basically, for example, A1 to B1, this is a ratio, is equal to A2 to B2, that you can also write as, based on what we saw over here, you can write it as you can see, A1 to A2 is not equal to B1 to B2. Therefore, here I can write A1 to A2 is equal to B1 to B2. And by the same, these are basically exactly the same ratios, or they mean the same thing. Also, based on the same logic, you can say that if you have A1 to B1 is not equal to A2 to B2, you can write the same thing as A1 to A2 is not equal to B1 to B2, right? So these are the kinds of things that you learn in mathematics class 6, 7, ratios and that sort of things, 6, 7 or 8, I suppose. So long story short, what that means is that basically here we said that the lines are supposed to have different slopes. The slope of the line, as we discussed here, is negative A to B, meaning that negative A1 to B1 is supposed to be not equal to negative A2 to B2. Negative and negative cancel out. A1 to B1 is not equal to A2 to B2, which means that A1 to A2 is not equal to B1 to B2. And this is the condition that we used in the previous chapters, in the previous classes, for a consistent system of equations, meaning that we said that A1 to A2 is not equal to B1 to B2, means that you have a consistent system of equations, meaning that the slopes are different. That in turn means that the lines intersect at a distinct point, and that in turn means that the system of equations is consistent and you have unique solutions, right? So now I'm going to use the same thing over here, the same basically condition, and let's see how we can use it actually. Now, if I write basically, if I write over here, basically, if I create a matrix out of this, let's see what we'll get. Okay, so now as you can see, so as you can see now, we can understand basically what this whole basically we understand how we can use this whole when we say that A1 to A2 is not equal to B1 to B2. So we calculate basically from this system, we make a matrix, meaning that we write 1 2 and 2 3, and that becomes basically matrix A. And then when we calculate the determinant A, the determinant A is basically the same matrix, just the determinant of the same matrix, meaning that you get 1 2 and 2 3, right? Now, if basically we know that in a determinant, if the elements of if the corresponding elements of any two rows or any columns is basically are exactly the same, we know that the determinant is equal to 0, right? Also, we know that basically if the elements of two rows or columns, the corresponding elements of two rows or columns in a determinant are in the same ratio, again the value of the determinant is equal to 0. And for the same reason, we say that basically when the value of the determinant is equal to 0, that the equation does not give you unique solutions, because that corresponds to a system where where you have, for example, some equation like x plus 2y is equal to 2, for example, and also you have, for example, something like for example, x plus 2y is equal to 3, right? So now these two lines correspond to a system of basically you can see that these two lines have the exact same slopes. So since they have the exact same slopes, that means that, and they're basically the C's here are different, meaning that the lines are apart from one another, but they have the same slopes, meaning that you would have a situation like this, for example. You have this line over here and this line over here. The two lines have exactly the same slopes, but since the C's are different, then the two lines are apart, meaning that the two lines do not coincide. If the two lines do not coincide, then of course this is an inconsistent system, because there is no point of intersection between the two lines. If there is no point of intersection, you have no solutions. And in this case, you can say that A1 to A2 is equal to B1 to B2 is not equal to, for example, C1 to C2. And if I write this in the form of a determinant, I will have basically, for example, 1 2 and 1 2. And as you can see, basically, as you can see, the matrix A would be this matrix. The two rows are exactly the same. That means that the determinant of A is equal to 0, which means that the system is inconsistent. It's not going to give you any solutions, right? On the other hand, I can have the situation where, for example, I have the exact same line as this line over here, x plus 2y is equal to 2. I have x plus 2y is equal to 2, and also again another line, x plus 2y is equal to 2. Now in this system, as you can see, again, A1 to B1 is equal to A2 to B2. And if I write a matrix out of this, again, I will get the same matrix, 1 and 2. And in this case, since the two lines coincide because you have exactly the same lines, then you have infinitely many solutions, right? This is again, in this case again, delta is equal to 0. Now I could have the situation where, for example, I have x plus 2y is equal to 2, and for example 2x plus 3y is equal to 5, and in this case you can see that a1 to b1 is not equal to a2 to b2, and that's not equal to c1 to c2, and what that means is that you can even forget about this part, but only this part where a1 to b1 is not equal to a2 to b2, and that means that you have a pair of lines that intersect at a unique point, at a distinct point, and this point of intersection is your solution. And so what that means is that here you can see that I can write this as a matrix 1, 2, and 2, 3. I write it as A, and then the determinant A is going to be equal to 3 minus 4, which is equal to negative 1, which is not equal to 1. And since the determinant of A is not equal to 0, in this case we say that basically A is non-singular. A is non-singular, and since A is non-singular, that means that A inverse exists. A inverse exists, and then in order to calculate basically the value of the matrix X, in this case we say that, for example, X is equal to A inverse times, for example, B, and that way we calculate the value of X and Y in this case, right? So that is basically the three cases that we get over here, and that is basically why we do all of those two cases and so on and so forth. I still have not got into the reason why we calculate the adjoint of A times B. Once I know that, I will let you know, of course. Okay, so now I have basically, we have figured this whole thing out here, and let me see if I can, let me write this, delete all of this so that we have some space here to work with. Okay, so now the system of equations that we want to solve here is x plus 2y is equal to 2 and 2x plus 3y is equal to 3. Now if you want to solve this system of equations, so you can form those matrices as A is equal to, for example, 1 and 2 and 2 and 3, and you know that your matrix X is equal to basically this matrix as X and Y, and you know that basically your matrix B is equal to, for example, 2 and 3, right? Now if I calculate basically the determinant of A, that gives me basically, I'll call it determinant A. If I calculate the determinant of A here, that gives me basically 1, 2, 2, 3, and that's equal to 3 minus 4, which is equal to negative 3, not equal to 0, right? And so that means that you have a unique solution. That is a consistent system. And you will have a unique solution. And why that is that you can see that in the case of your equations, basically the slope of the two lines are completely different. the slope of this line is basically m1 is equal to -1/2, and the slope of this line m2 is equal to -2/3. And since the slope of the lines are different, then that means that you would have basically two different lines, for example, something like this, and this would be, and this point, for example, would be their point of intersection. And that would be your solution, of course. Of course, this is just some two lines that I've drawn, not exactly these two lines, but to show you the idea. So whenever basically you have this type of situation where the two lines have basically a point of intersection, and therefore they have basically two different slopes, then the matrix that you create based on these coefficients of x and y, when you take the determinant of that matrix, the value of the determinant of that matrix is not equal to 0, and that shows you that basically the system is consistent and it's going to give you a unique solution, right? That's basically question number 1, and some reasoning behind why we do all of this business here. Question number 2, we have basically 2x minus y is equal to 5, and x plus y is equal to 4. So you can see that even without using matrices, I can see that basically the c's here are different, meaning that the lines are basically apart from one another, right? And I suppose this is when you take this equation and write it as 2x, for example, minus y is equal to 5, you can write this as negative y is equal to negative 2x plus 5, and multiply by negative 1, you'll get y is equal to 2x minus 5, and this 5 actually becomes which ultimately becomes a negative 5 in this form. This is your y-intercept, of course. This is the y-intercept of this plan, meaning that this is the point where the line actually goes through the y-axis, meaning that if you want to draw the graph of this line, you would have 1, 2, 3, 4, and 5, negative 5 here, and then you would the slope of the line is 2, meaning that for 1, basically when m is equal to 2 or 2 by 1, that means that this is your vertical change. This is your vertical change, and this is basically the horizontal change, or basically the ratio of vertical change and horizontal change. And what that means is that or some people call it rise over run. Some people call it rise over run, meaning how much you're vertically changing or you're rising, and how much you are horizontally changing or running across this axis, meaning that this would be running across the x-axis, and this would be basically rising across the y-axis, right? So what this means is that basically for 2 units of vertical change, you have 1 unit of, for 2 units of vertical change, you have 1 unit of horizontal change. Meaning that from this point, for example, if I have 1 unit of horizontal change, meaning that if I take this as 1 unit and come over here 1 unit of horizontal change, then I should have 2 units of vertical change, meaning that I will end up here, and the line is going to be some line like this exactly. And this is basically the line that the graph of the function, basically y is equal to 2x minus 5, or you can say 2x minus y is equal to 5, right? That is the graph of this function. Now, I have basically, I have the graph of this function here, and of course you can see that the y-intercept of this point is -4. The y-intercept of this line is -4. That means that this line goes through this point, and the slope of the line is actually in this form. When you write it, it becomes -a to b, a being the coefficient of x, b being the coefficient of y, which is -1 to 1, which is equal to -1. So that means that the slope here is -1. Now, if I say that x plus y is equal to 4, and I know that my y-intercept is -4, based on what we saw over here, +4 became -4, +5 became -5, so +4 becomes -4. I know that the slope is -4, and the y-intercept is -4, and I know that the slope is -1, meaning that if the slope is -1, that is -1 to 1, meaning that for 1 unit of basically vertical change in the negative direction, I have 1 unit of horizontal change. Meaning that for 1 unit of horizontal change changing from here to here, which is positive, I have 1 unit of vertical change in the negative direction. I have to come over here, which means that the line is going to be this line like this, which has a negative slope, right? And this point that you see here, this point of intersection is the point of intersection of the two lines, which corresponds to something about, for example, 0.5 -4.2, 0.5 -4.2, something like this. This is going to be the solution of this system of equations. So based on the lines, you know what sort of system you're dealing with, meaning that you know that this system is actually a consistent system. And I'm going to write 0.5 and -4.2 here in case we need it. And then what we will do is that now, instead of analyzing, you can also use the matrices that we have learned, meaning that you can, based on the equations that you have, you can write A is equal to, for example, 2, -1, and 1 and 1. And this matrix would be, if you take the determinant of A, the determinant of A would be 2 minus -1, which is equal to 2 plus 1, which is equal to 3, which is not equal to 0. Therefore, this is a consistent system. And you have unique solutions, a unique solution. Right? So basically A is non-singular, and A inverse of course exists. Here I can also say that A is non-singular, and A inverse exists, and the system of equations is consistent, right? Now, the next question that we have here is question number 3. And that is basically as follows. Okay, so now question number 3, we have x plus 3y. X plus 3y is equal to 5, and 2x plus 6y. 2x plus 6y is equal to 8. Okay. Now, as you can see, for example, in these equations, your y-intercept are different, meaning that the two lines go through the y-axis at different points, -5 and -8. but their slopes are the same, meaning that negative a to b here is negative 1/3. Here m1 is equal to negative 1/3, and here m2 is equal to negative 2/6, which is equal to negative 1/3. That means that they have the same slopes, but they go through the y-axis at different points, negative 5 and negative 8. That is one point, and that is another point. And their slopes are negative, and you can imagine that, for example, they have some slope like this. This is one of the lines. This is one of the lines, and they are parallel because they have the same slopes, which means that these two lines never actually intersect, and that means that you have no solutions. You have no solutions, and which means that this is an inconsistent system. Which means that this is an inconsistent system, right? So now to see that in terms of matrices, you can see that if I create a matrix using the information that I have here, I have 1, 3, and 2, 6, right? So that is basically A. Now in this matrix, if I calculate the determinant of this matrix, which is A, determinant A, I would have 1, 3, and 2, 6. And of course you can see that basically the corresponding elements of these two rows are in the same ratio, meaning that 1 times 2 is equal to 2, 3 times 2 is equal to 6, and therefore this is equal to 0. Since determinant A is equal to 0, therefore A is singular, is a singular matrix, and therefore this is an inconsistent system. So now what that means is that now at this point, if you didn't know about all of the things that we talked about in the beginning, meaning that, for example, that the two lines go through the y-axis at this point and this point, and the slopes are the same, and so on and so forth, now there would be two possibilities. Either you could have the situation where the lines basically are something like this, meaning that the lines go through the y-axis at two different points and they never intersect, in which case you have no solutions. And you could have the possibility that the lines are basically, for example, they have some situation like this where they go through the y-axis, but the two lines are coincident. The two lines are coincident, right? When they are coincident, you have infinitely many solutions, because well, the two lines basically intersect at infinitely many points, which means that you have infinitely many solutions. In this case, the two lines intersect at no point, which means that you have no solutions at all. Now, in order to decide which one of these is the case using matrices, right? Using matrices, you have to calculate the adjoint of A times B. Now, so basically I can say that in order to understand whether we have no solutions, 1, no solutions, whether we have no solutions, or number two, infinitely many solutions, we need to basically, and that is using matrices, and determinants, we need to calculate the adjoint of A times B. Now at this point I still don't know why we do this. I'll most probably, once we've gone through this exercise, by the time we've gone through this exercise, hopefully I'll know why, what is the logical conclusion of doing this operation, and then we will talk about it. But let's do this step and then let's see what happens. So over here we are saying that basically A is equal to this matrix as 1, 3, and 2, 6, and B is basically this matrix as 5 and 8, right? This is 5 and 8. Now what we need to do is that first we need to calculate the adjoint of B. The adjoint of B is basically a matrix that you calculate by basically when you have a 2 by 2 matrix, of course you can take you can basically take the 2 elements along the diagonal, and along the diagonal you will interchange the 2 elements, and for the other 2 elements you will just do the sign change, meaning that the adjoint of A in this case would be equal to basically 6, -3, and -2 and 1. 6, -3, and -2 and 1. And now if I multiply the adjoint of A by B, what I will have is 6, -3, -2 and 1, and I multiply that by 5 and 8. And as you can see, so what happens in terms of the equations that we had x plus 3y is equal to 5, and we have 2x plus 6y is equal to 8. And now as a result of doing this operation, 6 is being multiplied by 5 and -3 is multiplied by -8, right? So that would simply be 6 times 5 plus -3 times 8. And over here you will get -2 times 5 plus 1 times 8. So, and that would be a matrix, right? That would be a matrix. So now let's see what, and we argued here that if the adjoint of A times B, if that this matrix is not equal to O, we argued that if basically the adjoint of A times B is not equal to O, then basically no solution exists. No solution exists, meaning that the 2 lines are actually parallel and not coincident. two lines are parallel and not coincident. And we argued that if basically the adjoint of A times B is actually equal to the zero matrix, here you have basically two cases. You could have infinitely many solutions, which means that basically the two lines are coincident. The two lines are coincident, number one, and number two, again, you could have the case of no solutions. Meaning that the two lines are, again, you could say that the two lines are parallel and not coincident. Right? So I will take a screenshot of this because we will need to get back to this again to see how that goes. So I will now delete this thing. I will now delete all of these, and we will have access to them whenever we need to. So now what I'm going to do is that I'm going to calculate this, the adjoint of A times B, that is equal to basically 6 times 5 is equal to 30 minus 24. And over here you have negative 10 plus 8. And that is equal to basically 30 minus 24 is equal to 6. And this is negative 10 minus 8, which is equal to negative 2. And that means that basically this is not equal to O. When this is not equal to O, what that means is that basically you have no solutions exist, or the two lines are parallel and not coincident, which is actually the case in here, and we saw that on the graph of the lines as well, right? So now let's actually see what happens when we do this operation here, that we calculate the adjoint of A times B. When we calculate the adjoint of A times B, what we are doing is that we are taking this 6 and multiply it by 5, and meaning that I'm writing B2 times, for example, B2 times C2, and then I'm writing basically negative 3, which is negative basically B1 times 8. Negative B1 times 8, which is basically C2. So I'm actually doing this operation here. And then down here, what I'm doing is that I'm actually doing negative 2 times 5. Negative 2 times 5 is basically, this is A2, so that's negative A2 times 5, which is basically C2 times C2, and then I'm adding to that 1, which is A1 times, for example, times 8, which is basically 8, which is C2. So this is B2 times C2, meaning that if I write these equations as a1x plus b1y plus c is equal to c1, and if I write this as a2 times x plus b2 times y is equal to c2, so here I'm writing b2c2 plus negative b1 times c2. Let me see if I did this right. So here 6 times 5 would be, this is b2, and 5 would be c1. This is actually c1. And then negative 3 would be negative b1, and 8 would be negative and would be c2. This is correct. And then negative a2 times c2, so I'm calculating negative 2, which is negative a2 times basically 5, which is c1. That is c1. And over here I'm writing basically 1 time, so 1 is basically over here a1 times c2, right? So then we need to somehow see what that is in terms of and this is basically the adjoint of a times b. Okay. Now, if you're interested to know why that works, you can basically go into those equations and see what this becomes in terms of those equations. Now I'm going to just make a screenshot here, and then desktop, I'm going to call it system of equations matrix method, part 1, for example, on desktop. And I'm going to take a screenshot here. Come on. I don't know what to do with this. Okay, so let me write it down on a piece of paper. Okay, so now we know basically what is going on a little bit more. And so here you can say that basically, so we calculated the adjoint of a times b, and that is not equal to O, and so there is no solution of the given system of equations, meaning that system of equations is inconsistent. So and that corresponds to basically this case over here, which is basically this case over here. We said that basically the adjoint of a times b is not equal to 0, meaning that there is no solution, and so there is no solution for the given system of equations, right? So, and so here you can write therefore there is no solution for the system of equations. If you want to write more, you can say basically parallel lines and not coincident. Right, so that is basically what's going on here. Okay, so now let's do the fourth one as well. Okay, so now question number 4 is rather interesting, and I think we are going to need a little bit time on this video. So I'm going to basically end this video here, and then I'm going to show you how to graph these equations in a 3D dimensional system, although not on a 2D piece of sheet of paper, but using some tool that you can find on the internet. And so I'll end this video here, and then we will start with question number 4 in the next video. Thank you.